in April 2026. Keeping a billion-dollar AI data center from catching fire doesn't require, water or coolant. I mean, obviously the facility uses those, but the actual prevention, that requires a single pane of glass and just a whole lot of microsecond data.
Right, yeah.
So welcome to the control room. I want you to imagine, just for a second, that you are the operator sitting in that chair. You look through the reinforced glass, and you are surrounded by rows upon rows of multi-million-dollar AI hardware.
It is quite the visual.
Oh, absolutely.
Huh.
And the hum of the cooling systems is this, constant physical vibration in your chest.
Yeah.
You are in charge of all of this. The million-dollar question, or maybe the billion-dollar question, given the silicon sitting out there on the floor, is how you actually keep it all from melting down.
The sheer scale of what you are managing makes that an incredibly complex problem. You aren't just looking at a few isolated servers anymore. You are looking at thousands of interconnected, incredibly powerful GPUs processing data at speeds that, frankly, defy human comprehension. Without the right telemetry, you are essentially flying a commercial airliner through a hurricane while blindfolded.
Which is exactly why our mission today is so critical. We're taking a deep dive into a document that, on its surface, might sound like a cure for insomnia if you aren't initiated.
Oh yeah, the title alone is a mouthful.
It really is. We have in front of us the SuperCloud Composer, or SCC Performance Metrics User Guide, Release 3.1.2.0.
Quite the page turner.
I know, right?
Yeah.
But this is literally the Rosetta Stone for understanding how operators actually monitor the pulse, the temperature, and the raw power of the world's most advanced computing infrastructure.
Okay, let's unpack this. What exactly are we looking at when we talk about the SEC dashboard?
So the SuperCloud Composer is, at its core, a highly customizable Grafana-like analytics interface.
It's the visual layer. It provides data center operatives with complete oversight of their GPU workload operations and, their storage clusters, too. It takes all this complex metadata and presents it in a digestible format. But the architectural nuance here, that is what makes it resilient.
Yeah, that architecture section of the manual really made me pause.
Yeah.
Because the SEC itself doesn't actually collect the data, right?
Exactly. The manual explicitly outlines that SEC relies heavily on external exporters. It supports NVIDIA DCGM, that's Data Center GPU Manager, and Wakaya storage clusters.
Wakaya.
But the actual metrics data, that is collected by an external Prometheus server and dedicated exporters.
See, it feels like hiring an external independent accounting firm to meticulously go through all the receipts, do the hard math, and then just hand the final numbers over to the CEO. And the SEC is just the CEO's presentation board making it look pretty.
That's actually a really good way to frame it.
But I have to push back here a little bit. Why build it this way? I mean, why not just have the SEC do everything, collect the data, analyze it, display it? It seems like adding a middleman for no reason.
Well, integrating the collection and visualization layers into a single, massive, monolithic application creates a massive single point of failure.
Oh, I see.
Right, by relying on Prometheus, which, by the way, is the industry standard for time series event monitoring supermicro, allows data centers to utilize a decoupled architecture.
So they're entirely separate systems.
Completely separate. You configure this in the SEC admin settings by simply providing the Prometheus IP address and port number. That's it. If the SEC visualization layer crashes or needs a rolling update, your data collection layer is entirely unaffected.
Wow.
Prometheus is still out there, scraping telemetry, logging errors, triggering automated alerts.
That decoupled approach makes perfect sense. I mean, you don't want the security cameras to stop recording just because the monitor in the security booth got unplugged, right?
Precisely.
The underlying data must survive the UI layer going down.
It also allows the SEC to be incredibly lightweight. The visualization engine doesn't have to spend its own precious compute cycles parsing raw binary data from a PCI disk.
Right, it just paints the picture.
Exactly. It just queries the time series database and renders the widgets.
So since SEC is just the visualization layer, we really need to know exactly what kind of hardware telemetry it's pulling from that database. We need to kind of step into the engine room here.
We do. And the 2026 user guide focuses on the absolute bleeding edge of hardware. We are talking about granular telemetry for very specific microarchitectures.
Yeah, I was looking at the drop-down menus in the manual's screenshots, and it explicitly lists the NVIDIA B200 specifically the 180 GDB HBM3E model and the NVIDIA B300 SXM6AC.
Yeah, those are absolute monsters of compute.
Monsters. We are talking about silicon that draws immense power.
And the metric types tracked for these specific GPUs go way, way beyond basic CPU load percentages. The guide details tracking SM clock frequency and memory clock frequency down to the megahertz.
The SM being the streaming multiprocessor, right?
Correct, the core workhorse of the GPU. But the thermal metrics are where the physical reality of the data center really comes into play.
Yeah. The manual lists memory temperature and overall GPU temperature, but it extended the energy level in a way that honestly shocked me. Power draw in watts is standard, I expect that. But then there's a total energy consumption since boot, measured in millijoules.
Yes.
Millijoules. Why on earth does an operator need to track energy in millijoules? It seems so excessively microscopic.
But what's fascinating here is the economic scale of AI training. You have to remember, when you are running a 100,000 GPU cluster, a fractional variance in energy consumption per cycle equates to massive differences in utility costs.
Oh, wow.
And thermal output. Tracking in millijoules allows automated systems to calculate the exact power efficiency of a specific algorithmic workload.
So they can see exactly how much power a specific math problem takes to solve.
Exactly. And it tracks this since the driver was last reloaded, giving a perfect baseline for a specific, isolated training run.
It's like looking at the dashboard of a Formula One race car. You aren't just looking at the speedometer. You're looking at the exact temperature of the front left tire tread, and you are calculating the fuel burn per microsecond to determine if you could finish the lap without pitting.
That is a very apt comparison, but, an F1 engine is only part of the equation.
Right.
The transmission of that power to the wheels is just as critical. In a data center, how the data gets to the GPUs dictates the entire performance of the cluster. The compute is essentially useless if it's starved of data.
Which brings us to the PCIe and NVLink superhighways.
Yes. The manual heavily emphasizes data transfer metrics. For the PCIe bus, which is the connection between the GPU and the host system, the SEC tracks the number of bytes of active PCIe TX, or transmit data, and RX, which is read data.
And it specifically notes this is from the perspective of the GPU, which is an important distinction.
It is.
It also tracks the total number of PCIe retries. I imagine that's the metric operators lose sleep over.
Oh, without a doubt. A retry is a physical failure in the data transmission. It means the data was sent, encountered an issue like signal degradation or a packet collision, and the hardware had to pause and send it again.
And in an AI context, pausing is very bad.
In an environment where you are training massive language models, time is literally measured in millions of dollars of compute. A high retry rate indicates a failing component or severe electromagnetic interference on the board itself.
And it's not just the host-to-device PCIe connections we're looking at. The NVLink metrics are even more intense.
Yeah.
For anyone managing these clusters, NVLink is the proprietary high-speed interconnect, letting these B200s talk directly to each other, right? Bypassing the host CPU entirely.
Exactly. When you have a pod of B200s, they must function as a single logical unit. They share memory and distribute the neural network weights across the entire cluster. So the SEC tracks the NVLink bandwidth counters for all lanes in bytes per second.
But the critical telemetry really lies in the error reporting, doesn't it?
It does.
Yeah, I'm looking at the list here. Total number of NVLink flow control CRC errors, data CRC errors, retries, and recovery errors.
Let's break that down. A cyclic redundancy check, or CRC error, means the data was corrupted in transit. The sender calculated a checksum, the receiver calculated a checksum, and they simply didn't match.
So the data arrived garbled.
Yes. And if your GPUs cannot exchange data cleanly, the entire cluster stalls waiting for clean data to arrive. An operator watching the SEC dashboard isn't just looking at how fast the SM clock is running. I mean, that's important. But they're watching those NVLink recovery errors to see if the internal network of the pod is silently collapsing under its own weight.
So we've seen what happens when the hardware is running perfectly, or, well, at least trying to. But what happens when it's pushed beyond its limits? How does the SEC dashboard warn the person sitting in that control room that the hardware is taking defensive action?
The manual actually dedicates significant space to throttling metrics, because throttling is a self-preservation mechanism.
Right.
The hardware deliberately degrades its own performance to prevent catastrophic physical damage or just general system instability.
And the SEC tracks throttling duration in microseconds. And just the precision is wild to me.
Well, the system operates at microsecond scale, so the reporting must match that reality. The dashboard breaks down the specific reasons for the throttling, too. You have throttling duration, due to power constraints, meaning the GPU hit its absolute power cap and had to step down.
Okay, that makes sense.
You have thermal constraints, meaning it's physically overheating and trying not to melt.
Right. There are also board limit constraints and reliability constraints listed here.
Yeah.
But I have to stop you on one specific metric I found in the manual.
Oh.
Yeah. Throttling duration due to low utilization. I stared at that for a while.
Yeah.
Why would a machine throttle itself because it's being used too little? If it's not being used, isn't it already doing nothing? I don't get it.
The assumption that an idle machine draws no power is a very dangerous one in infrastructure management. Oh, absolutely. A modern B200 GPU drawing hundreds of watts at baseline will still generate massive heat and consume incredibly expensive electricity, even when it is just waiting for data. If the GPU is sitting idle, perhaps because it's waiting on a slow storage drive or a network bottleneck, it actively steps down its power state and its clock speeds.
Okay, so it's actively shifting gears.
Yeah.
Like a modern car engine that deactivates cylinders when you were just cruising on the highway to save gas.
Yeah.
It's intentionally throttling its potential to match the low demand at that exact microsecond.
Exactly. The physical reality of running tens of thousands of GPUs is that idle power draw can cost millions of dollars a year. So low utilization throttling is an efficiency mechanism.
There's a catch,
A
right?
huge one. For the operator staring at the SEC dashboard, high levels of low utilization throttling during a massive training run is a giant red flag.
Because it shouldn't be idle.
Precisely. It tells you your incredibly expensive GPUs are starving for data. They are sitting there twiddling their thumbs, powering down to save electricity because the network can't feed them fast enough.
That is brilliant. It's essentially a diagnostic tool masquerading as a power-saving feature.
It really is.
But here is where the user guide throws a massive curveball. We've just discussed all these incredible granular metrics. But if you look at sections 2.1.1 and 2.1.2 of the manual, you realize that the SEC dashboard is dealing with the massive hardware blind spots. Not all GPUs are created equal.
No, they're not. The illusion of a single pane of glass completely shatters when you introduce mixed vendor hardware or even just generational gaps.
Right.
The SEC dashboard is entirely dependent on the in-band data exposed by the hardware manufacturer's own APIs.
Okay, and the manual points out the NVIDIA H100 exceptions. Now, the H100 was the absolute king of the hill just a few years before this 2026 manual was published. It was the standard. But if you plug an H100 into the SEC, you get no records found for 16 different critical metrics.
The omissions are honestly glaring. For example, the H100 cannot display the number of bytes of active PCIe TX or RX data through this specific interface.
Wait, really? You are completely blind to the superhighway traffic?
Completely blind. You also lose visibility into the self-preservation mechanisms we just discussed. The H100 integration doesn't support reporting the throttling durations.
Are you serious?
Yeah, you cannot see if it's throttling due to power, thermal, sync boost, or those low utilization constraints. The dashboard just won't show it for that chip.
That is terrifying for an operator trying to diagnose a slowdown. Hey, why is the cluster slow? I don't know, the H100 won't tell me.
It gets worse. The situation with error correction is even more problematic. The integration doesn't support reporting the total number of single-bit or double-bit volatile ECC errors, nor the persistent ECC errors.
Oh, wow. ECC memory is critical for preventing silent data corruption. I mean, volatile errors might just be a random cosmic ray flipping a bit, right? Which the system corrects and resets on a reboot. But persistent errors, that means the physical silicon in the memory module is fundamentally degrading.
Exactly. And if you can't see persistent ECC errors, you cannot proactively replace a failing GPU before it completely crashes a multi-million-dollar training job. You are just waiting for it to fail.
And furthermore, the H100 doesn't report the NVLink CRC errors or recovery errors to the SEC dashboard. An operator managing a rack of H100s is essentially flying half blind compared to managing the newer B200s.
It really highlights the pace of API development on the hardware side.
But then we get to the AMD MI300X exceptions. And this list, while it's shorter, it is almost comical in how critical the missing data is.
The MI300X integration with SEC for in-band data reveals a stark contrast in vendor API philosophies. The manual lists 7 metrics that will simply show no records found.
Let me read these off because it's shocking for a modern data center. No memory clock frequency.
Right.
No GPU clock frequency. No GPU memory usage. No GPU power capping. No GPU power consumption. No GPU utilization. And worst of all, no GPU temperature.
Yes. The absence of temperature telemetry for a high-performance compute accelerator is a profound operational challenge.
How do you run a pod of MI300Xs without knowing if they're physically melting? I mean, do you just guess?
Well, this brings up a larger issue in infrastructure management. The SEC documentation notes that some tooltips and metrics actually come from out-of-band data via the Supermicro BMC, the baseboard management controller.
Okay, what's the difference there?
In-band data comes from the operating system level, right? It's querying vendor-specific tools like NVIDIA DCGM or AMD ROCm. Out-of-band data comes directly from the motherboard's dedicated management chip, completely bypassing the main OS.
So the temperature data isn't gone, it's just not feeding into the beautifully aggregated SEC dashboard through the standard in-band pipeline.
Exactly. For a data center manager running a mixed environment, say you have NVIDIA B200s for training and AMD MI300Xs for inference, this vendor discrepancy is an absolute nightmare.
I can imagine.
Your unified dashboard suddenly has giant opaque gaps in it. You have to rely on completely different tools or query the out-of-band BMC network just to verify your AMD chips aren't thermal throttling, while your NVIDIA chips are over there reporting their internal network retries down to the microsecond.
It's so disjointed. The operator has to possess a deep, almost instinctual understanding of the specific limitations of every single hardware generation in their facility.
They do. It's a highly specialized skill set.
But let's assume for a moment you do have perfect telemetry. All the APIs are cooperating. You are sitting in the control room, and there are 10,000 GPUs out on the floor. How does a human operator even begin to comprehend that volume of data? You obviously can't have 10,000 line graphs on one screen.
No, the human cognitive limit necessitates heavy data aggregation. The SEC manual actually details two distinct quantitative data collection types, the GPU level and the appliance level.
Right, the GPU level, which the manual calls the unit level, is straightforward. You are looking at the raw metric for a single physical GPU card, G1, G2, G3.
Right, but managing at the unit level doesn't scale. If you have 10,000 units, you can't monitor unit by unit. The appliance level is where structural management occurs.
Define appliance in this context for the listener.
An appliance is a system chassis containing multiple GPUs, often 4 or 8 in a single box. The SCC dashboard allows the operator to aggregate the telemetry of all the GPUs within that physical chassis using 4 distinct mathematical functions: max, min, sum, and average.
The manual gives a really clean example of this using GPU temperature for a 4-GPU appliance. It assumes we have G1 at 30 degrees Celsius, G2 at 43, G3 at 55, and G4 running hot at 70 degrees.
And depending on the mathematical function you select for your widget, the dashboard changes its narrative entirely.
Okay, let's hear it.
Max returns 70, min returns 30, sum aggregates the total thermal load to 198, and average smooths the data out to 49.5 degrees.
I was thinking about this, and it's a lot like managing a team of sled dogs in the Arctic.
Oh.
Yeah, if you are the musher, looking at the average pace of the dogs is great for estimating when you'll reach the next checkpoint. But average temperature is a highly dangerous metric in certain contexts. The average temperature of 49.5 degrees across those 4 GPUs sounds perfectly healthy, right? The dashboard stays green. But the max temperature of 70 tells you that one specific dog, one specific GPU, is approaching a thermal limit and is about to collapse.
That's a great analogy. And this raises an important question for you, the listener, if you are designing these monitoring systems. Which metric dictates your automated response?
Right.
If your objective is preventing a catastrophic hardware failure or a thermal runaway event, you must monitor the max temperature across your appliances. You script your cooling systems to react to the highest localized heat source.
But if you are the CFO trying to calculate the power usage effectiveness, the PUE of the facility, you don't care about the maximum temperature. You want the sum or average of the power draw across the entire fleet to calculate your utility bill.
Exactly. Choosing the wrong aggregation function can completely mask critical failures. An average can hide a single GPU that is literally on fire, just as a maximum can falsely trigger a facility-wide cooling surge for a single localized hotspot.
Context is everything. Now, speaking of masking critical failures, we need to transition to the other side of the data center equation. We've established that a low utilization throttling alert means the GPU is starved for data. It's like having an F1 engine with a clogged fuel line.
Yes.
Let's talk about the storage metrics, because SEC doesn't just watch the compute, it watches the data flow.
The SCC tightly integrates with Wakaio storage clusters. In modern AI workloads, the storage layer is frequently the primary bottleneck, and the telemetry here goes far, far beyond traditional IT metrics of simply checking how much free space is left on a hard drive.
Oh, totally. The storage metric types table is entirely focused on flow dynamics. It tracks cumulative read and write IOPS input-output operations per second. It monitors throughput in bytes per second, and critically, I/O latency.
It also measures the immense computational strain placed on the storage hosts themselves. The manual details tracking host FE core utilization rate, host compute core utilization rate, and host drives core utilization rate.
This specific breakdown really highlights the complexity of modern storage. It wants to know exactly which part of the storage pipeline is sweating. But how does a host FE core differ from a host drive core, and why does an operator care during an outage?
Well, the FE or front-end cores handle the network connections and client requests coming from the GPUs.
Okay.
The drive cores, on the other hand, are responsible for the physical interaction with the flash media itself. They manage the read and write cycles and the garbage collection on the SSDs.
So they separate the control plane from the data plane.
Essentially, yes. If an operator sees the host FE core utilization spiking to 100% while the drive core utilization is low, it means the network layer is overwhelmed by the sheer number of concurrent requests from the GPUs.
Even though the physical hard drives have plenty of bandwidth to spare?
Exactly. You have a networking bottleneck at the storage node, not a physical drive bottleneck.
To really understand this storage architecture, I spent a lot of time in the back of the manual. The glossary in this user guide is an absolute goldmine for understanding the physical evolution of the data center. It demystifies how these massive storage clusters actually feed the B200 GPUs.
The terminology in the glossary reflects a massive paradigm shift away from traditional server architecture.
My absolute favorite acronym in the entire document is JBOF, just a bunch of flash.
It sounds colloquial, but it represents a serious architectural
Oh,
concept.
that sounds like a joke, but it's not.
No, it's very real. A JBOS is a physical chassis entirely populated with NVMe flash storage. It contains no heavy compute processors, no application logic. It is pure, unadulterated, high-speed storage capacity.
But how does a dumb box of flash memory talk to the smartest GPUs on Earth fast enough to keep them from throttling? That's where NVMeOF comes in. Non-volatile memory express over fabrics.
Yes.
The glossary defines this as allowing the disaggregation of NVMe drives through a network fabric.
This is the critical leap we've taken in recent years. Historically, data centers relied on direct attached storage, or DAS.
Where the hard drives lived inside the same physical server box as the CPU and GPU?
Exactly. But DAS simply doesn't scale. With NVMeOF, the storage is physically disaggregated. The JBOF chassis might be sitting 3 aisles over from the GPU racks, but it communicates over a specialized network so rapidly that the GPU's operating system believes the hard drive is plugged directly into its own local motherboard.
And the secret sauce making that illusion possible is ROCE. ROCE RDMA over Converged Ethernet. The manual defines RDMA as Remote Direct Memory Access. It permits direct memory reads from the memory of one computer into another, without the operating system getting involved at all.
Bypassing the OS kernel is the only way to achieve the microsecond latency required.
I love this concept. Imagine a massive traditional library. Normally, if you want a specific piece of information, you go to the front desk, fill out a request form, and hand it to the librarian who, in this analogy, represents the operating system kernel.
I like where this is going.
Right. The librarian takes the form, processes it, walks back into the stacks, locates the book, brings it back to the desk, and hands it to you. The sheer amount of bureaucratic overhead introduces massive latency.
Every context switch between user space and kernel space consumes CPU cycles and adds microsecond delays. It adds up fast.
Exactly. But ROCE and NVMeOF fundamentally change the rules of the library. It gives the GPU a direct VIP pass to bypass the front desk entirely. The GPU sprints straight into the storage stacks, reaches directly into the memory of the JBOF chassis, grabs the exact data it needs off the shelf, and runs back out. It completely removes the bureaucratic middleman.
It has to. The latency introduced by asking an operating system's network stack to handle standard TCP/IP storage requests is simply unacceptable when training massive neural networks. The data must flow directly from the flash memory into the GPU's HBM3E memory.
And the SEC is watching all of this.
Yes, the SEC monitors the latency of those exact RDMA transactions. If your ROCE latency spikes, your GPUs starve, and your low utilization throttling alarms start going off, everything is deeply connected.
We have all this telemetry flowing in. I mean, we have microsecond throttling data, NVLink CRC errors, distinct FE core utilization, ROCE latency. It's a flood. But if you just have endless streams of raw numbers scrolling down a terminal screen, human error is inevitable.
Humans are not built to parse scrolling code during an emergency.
Exactly. We need to talk about building the cockpit. How does the SEC translate this incredibly dense telemetry into a user experience that actually prevents cognitive overload?
The SEC documentation outlines specific performance statistical types. These are the visual widgets operators use to construct their customized dashboards. You have the time series line chart sampling, which maps a metric across X and Y axes over a historical window.
Classic line graph.
Right. You also have the min-max ABG sampling table, which pairs that line graph with a definitive text table of the extreme values so you don't have to guess.
There is also the gauge meter, which looks like a traditional analog speedometer on a car, giving a sense of physical limits. The raw data table, the status widget, which provides a binary text state like started or healthy, and finally, the pie chart.
The UX design rules outlined in the manual are very rigid about when and how to deploy these visualizations. They don't want operators just throwing charts up randomly.
Right.
For instance, regarding GPU metrics, a multi-lines chart is strictly designated for the unit level, showing every individual GPU's trajectory. A single line chart is exclusively for the appliance level, showing the aggregated sum or max.
See, the visualization rule that really caught my eye was regarding the storage metrics. The manual explicitly states that the pie chart is applicable only for the protection status metric type.
That's right.
It shows a circle broken down by 0 failure, 1 failure, or 2 failures, and that's it.
The psychology behind restricting the pie chart solely to failure status is fascinating.
I was wondering about that. Why wouldn't they use it for utilization or power distribution? Why restrict it only to failures?
Because a pie chart connects with human psychology on a primal geometric level. It instantly communicates structural integrity. If you are looking at a line graph tracking drive failures over time, your brain has to perform cognitive work.
What do you mean?
You have to read the axes, check the scale to see if the line represents 1 failure or 100, and evaluate the trend line. That takes precious seconds.
But a pie chart is absolute.
Yes. If that circle is not 100% solid green for 0 failures, if you see even a sliver of orange or red, your brain instantly recognizes that the whole has been compromised. A piece is missing.
It's instinctual.
Exactly. During a Severity 1 infrastructure incident, when alarms are blaring, minimizing the operator's cognitive load is paramount. Immediate threat detection trumps detailed trend analysis in that initial second of crisis.
That is brilliant UX architecture. It's not about aesthetic variety. It's about engineering human reaction times. And the dashboard management itself has physical screen real estate constraints as well. The manual details different chart sizes. Extra large spans 6 columns across the interface. Large is 4 columns. Standard is 3. Small is 2 columns.
An operator cannot simply pin every metric as an extra large widget. They are forced to curate.
You only have so much screen space.
They have to decide what telemetry is structurally vital to their specific cluster and allocate the visual real estate accordingly.
And the operator must also be deeply aware of the technical limitations of the dashboard software itself. The guide contains a massive caveat regarding the data refresh rate.
Yes. Section 2.3.
Yeah. The SEC allows you to set auto-refresh intervals ranging from 10 seconds up to 1 hour. But there is a crucial limitation written in italics in the manual. Only last time period supports data refresh.
This is a fundamental limitation of querying time series databases. If you are using the date picker to investigate historical data, say, you are performing a post-mortem on a massive thermal throttling event that occurred at 3 a.m. on Sunday, the auto-refresh function is hard disabled.
You cannot auto-refresh a static window of the past. It just doesn't make sense.
Right. And attempting to auto-refresh a complex historical query every 10 seconds would place an immense, completely unnecessary computational load on the Prometheus server. The dynamic refresh is reserved exclusively for the bleeding edge of the live data stream.
So what does this all mean? When you step back from the microsecond throttling data and the pie charts and look at the SuperCloud Composer Release 3.12.0 user guide as a cohesive document, it paints a very specific picture of the modern infrastructure professional.
It really does.
They aren't traditional IT staff swapping out broken RAM spics anymore. They are pilots navigating massive, interconnected physical forces. And the SEC is their single pane of glass, giving them real-time, aggregated oversight of both the blazing compute engines and the disaggregated fuel tanks feeding them.
If we connect all of this microtelemetry back to the macro picture, the ultimate endgame of this technology is defined right there in the glossary under CDI. Composable disaggregated infrastructure.
Composable disaggregated infrastructure.
Right.
Sounds like science fiction.
It sounds like it, but it is the reality of the modern data center. The manual defines disaggregated infrastructure as the physical separation of core components, compute, storage, and networking.
Okay.
Instead of buying rigid, pre-configured servers that contain exactly 2 GPUs, 2 CPUs, and 4 hard drives inside a single metal box, you purchase vast pools of raw resources.
So you have an entire rack of nothing but B200 GPUs.
Right.
And another rack across the room is entirely JDOF flash storage. Another rack is pure networking switches.
Exactly. CDI allows the orchestration software to logically assemble these separate physical components on the fly during a system's provisioning phase.
Wait, on the fly.
Yes. If an AI research team needs to train a massive model this afternoon, the software logically composes a bespoke supercomputer out of 64 GPUs from Rack A, 500 terabytes of flash from Rack C, and connects them instantly over the ROCN network.
It is exactly like playing with digital Lego bricks, except every brick costs tens of thousands of dollars, and they have to communicate in microseconds.
That's a perfect way to describe it.
And SEC isn't just watching static physical computers. It's monitoring fluid, disaggregated components that are constantly being assembled and disassembled in real time to maximize the return on investment of the silicon.
With telemetry must be flawless because the physical architecture of the computer itself is changing hour by hour based on the workload demands.
That is wild. It fundamentally redefines what a computer even is at that scale.
Yeah.
Well, that brings us to the end of our journey through the SEC manual. But I want to leave you, the listener, with one final thought to mull over.
Let's hear it.
We've just spent this deep dive exploring the extensive, almost biological telemetry that human operators use to monitor AI supercomputers. We're talking about humans tracking microseconds of sync boost throttling, agonizing over single-bit persistent ECC errors, and relying on pie charts to instantly recognize structural failures.
Right.
But with metrics this dense, this fast, and this complex, how long until these dashboards are no longer built for human eyes at all? As we move toward fully composable disaggregated infrastructure, how long until this fire hose of Prometheus telemetry feeds directly into an AI model, allowing the data center itself to autonomously monitor, throttle, dynamically compose, and physically repair its own architecture in real time?
That is a profound question.
How long until the human operator is no longer sitting at the command console, but is instead left standing entirely outside the glass control room, just looking in as the machines manage the machines? Keep digging into your own sources, keep asking the hard questions about the infrastructure around you, and we will see you on the next deep dive.